Hey, welcome to Chapter 10. I hope you enjoyed the work with quadratic equations. We're now going to look at another part of algebra which is really important, which is when linear systems is what we call it, but it has to do with when things overlap. Are there solutions that apply to different situations? The discussion here about swimming is illustrative of that. It shows a set of data for men's time and women's time for the 100-meter freestyle swimming. You can see that using linear regression, as you plot out the times, it appears that the women's time are improving faster than the men's time, which leads you to believe at some point they will intersect. And you can take the equations, and they're given in the text, plot those lines, and you can see the intersection by graphing. We can also solve for this algebraically and find out when are the two equations equal to each other. That's really what it means when we are finding that out. The other part that you might want to ask yourself is, will this really happen? Will there be a tapering off in times? And in both cases, it would seem to indicate that the times will progress, and at some point way in the future, they will finish as soon as they start. In other words, times will go to zero, which doesn't seem likely at all. But this is the idea of linear systems. Let's get on to the lesson. An introduction to systems. The idea of solving a system of equations means finding all of the solutions that are common to the equations. There's some text here. I put it in to read it to you. I wanted you to see it, which says that a system is a set of equations or inequalities joined by the word "and" that together describe a single situation. The two equations at the beginning of this chapter describing the winning Olympic times of men and women in the 100-meter freestyle events are an example of a system of equations. Systems are often signaled by using a left-hand brace. There it is, in place of the word "and." So we can write this system as, we've got our brace, then it says y equals, and a negative 0.1627 times x plus 372.99, and y equals, and it gives the next equation. When you write a system in this way, it is helpful to align the equal signs under one another. This just helps in managing the information. There is some vocabulary for this lesson. You should know it. Please take a look. Also, as you're going through this, please read through the lesson. Make sure you know what is going on with it, and you really need to know what a system of equations is. Okay, here we've got a system. Let's look at what we might figure out about this. This is example 1. This is in addition, of course, to what's in the book. So consider the system below. Y equals 4x minus 11 and 5x plus 2y equals 4. And it asks you first to verify that the ordered pair 2, negative 3 is a solution to the system. Well, the first thing we can do is, by verifying this, is to plug it into both equations and see if they both work. Are they both true using this ordered pair? And that would mean if true, then it's a possible solution. So for our upper equation, we have negative 3 equals 4 times 2 minus 11. And 2 times 4 is 8. Negative 3 equals 8 minus 11. Negative 3 equals negative 3. Good, we've got it done here. It works. So our first problem checks. Now for our second problem, 5 times 2 plus 2 times a negative 3 equals 4. So that's 10 plus a negative 6 equals 4, and 4 equals 4. It checks. We have verified that it is a solution to the system of equations. The second part is show that 1, negative 7 is not a solution to the system. Now, for this problem, we only need to verify this for one of them. If it doesn't work for one, it's not part of the system. We don't need to show that it doesn't work for the other one. So we'll start with the y equals 4x minus 11. So 1 equals 4 times a negative 7. Whoops, I got that backwards. Let me fix that. A negative 7 equals 4 times 1 minus 11. And that says that a negative 7 equals a negative 7. So that checked for our upper one. It checked. Let's go to the next. So 5 times 1 plus 2 times a negative 7 equals 4. 5 plus a negative 14 equals 9, not 4. And so this does not check. Therefore, 1, negative 7 is not a solution to the system. It has to check for both equations in order for you to verify that it is true for both for the system. Okay, next one. We've got the problem to solve. So a box of chocolates has 20 pieces of candy. There are 6 more chocolates with nuts than chocolates without nuts. Using a graphing calculator, solve a system of equations to determine how many chocolates have nuts and how many do not. Okay, example 2. A box of chocolates has 20 pieces of candy. There are 6 more chocolates with nuts than chocolates without nuts. I like chocolate. Using a graphing calculator, solve a system of equations to determine how many chocolates have nuts and how many do not. Well, I got the graphing calculator up, but we're not ready for it because we don't know what to put in for an equation, right? I mean, let's go to graph. And f sub 1 of x, I don't know what that is. So I need to figure that out before I go any further. Let's parse it. A box of chocolates has 20 pieces of candy. So I got 20. 20 equals, and there are more chocolates with nuts than chocolate without nuts. So I need a variable for each of those. I'm going to use C for chocolates, and for chocolates with nuts, I'm just going to use N. So 20 equals the number of chocolates without nuts plus the number of chocolates with nuts. That's total is 20. I also know there are 6 more chocolates with nuts than chocolates without nuts. So I know that my chocolates plus 6 equals my chocolates with nuts, right? There are 6 more chocolates with nuts than chocolates without nuts. So chocolates, total chocolates plus 6 more would give me my total chocolates with nuts. Okay, so I've got 2 equations. I need to put them in an f of x form or a y equals form so I can have a system of equations that I can enter into the calculator. This is a system of equations. It's just not in a form that I can enter into the graphing calculator. For this first one, the second one, C plus 6 equals n, that's in a form I can use because I've got it in the n. If n is my y value or my function of value, then I can use that. So I'm going to make this one, we'll call this f sub 2 of n, not of n, of c. And when we get to the calculator, we'll have to put in an x here, right? Ooh, bad writing day, guys, here. Okay. F sub 2 of c equals c plus 6. Okay, I've got it. So here I need f, I'm going to make this f sub 1 of c equals, and I want to be left with n, right? So this is going to be 20 minus c. So the number of chocolates, 20, total number of candies is 20 minus the number that are just chocolate equals the number that are with nuts. So here I have a system, and now I have something I can enter into the calculator. You might be looking at that thinking you see another way to solve it, and the answer is yes, there are a lot of ways to solve these. Right now we're using the calculator. This is useful for a time when you can't see how to solve it, but you can calculate it and graph it and see what you get. So f sub 1 is 20 minus x, right? We've got to use our x value. And we'll enter that. I don't see anything. Well, my y-intercept will be 20, right? And my x-intercept will be 20. So I'm going to go with that. So window, settings, x minimum, I don't really need to see down to negative 10, so I'm going to go maybe to negative 2. Let's try that. Our max will be 20. Our y value, we're going to go also with negative 2, and y max will be 20. Okay, and I've got a graph now. I can see what's going on. So that's the graph of the f sub 1, c equals 20 minus n. We need another graph for our next function. And in this function, it's c plus 6. And remember, we're substituting x. So x plus 6. Enter. And I now have a graph that shows me the intersection of these two. Now, from that, I need to know, I'd like to know where this falls. So I go to my intersect command, analyze graph, intersection. I pick the lower bound, upper bound, and it tells me that my intersection of this is 7, 13. There are 13 chocolates with nuts and 7 chocolates without. Okay, that's solving a system of equations by graphing and using a graphing calculator to solve the problem. Next up is our guided example, which is example 3 in this in your book, and this says to find all solutions to the system y equals a negative x plus 4 and y equals a negative x minus 2. It asks you to graph both equations using a graphing calculator. How many times do the lines appear to intersect? Well, that's our first question, but we need to get a graph up. So I'll pull up the graphing calculator. We'll go ahead and I'll open up another document on this. Sorry. Okay. We're going to add a graph, and so here's our f sub 1 of x, and that's going to be equal to negative x plus 4. So the opposite of x plus 4 is my first function, And for my second one, opposite of x, the opposite of x minus 2, and enter. And there I've got my two graphs. And looking at the image here, it appears that they don't intersect. I don't know. Do I know that they don't? Do I need more information? Well, we know something about slope. We've studied slope. What do we see about the slope of these two lines? Well, they're the same. So if their slopes are the same, then they're always going to be parallel to each other, and they're never going to intersect. So our answer to our first question is, how many times do the lines appear to intersect? That would be 0. What's the slope of each line? Well, the opposite of x is a -1 times x, right? So that means the slope is -1, and we could probably figure this out by looking at the graph and determining the slope through that, or we could calculate slope, but we know that it's -1 times x. We know what slope is, so the slope of the line is -1. If two lines in a plane do not intersect, they are called what? I just said it. Parallel. Parallel lines never intersect. Look at the table of values in the graphing calculator. Is there an ordered pair common to both lines? Well, we can go to the graphing calculator. Menu, table, split screen. I now have a table that I can look at, and it asks us to determine if there's any intersection, and we know that there won't be because we know about parallel lines and graphs. So the answer to that is there isn't one. Is there an ordered pair in common to both lines? The answer is no. There's not. They're parallel. They never intersect. This is an example of a solution of a system of equations for which there is no solution. The solution set is the null symbol. We can use the null symbol. We can use the set brackets with nothing in it. We don't put a null symbol in that. This means null, the set brackets with nothing in it. The null symbol means a null set. A null set is weird, so don't do it. So that's it. That's example 3. Got one more example for you for this lesson. This is our example 4. Cafe. A cafe has a monthly fixed cost of $4,700, and a typical customer order costs the cafe $2. Therefore, the cost to serve X customers in a month is given by Y equals 4,700 plus 2 times X. The typical order costs the customer $10. So the revenue equation is Y equals 10 times X. Find the break-even point for the cafe using your graphing calculator. Well, let's see. We got everything we need. It's in our Y equals form. So our system of equations for this will be f sub 1 of x equals 4,700 plus 2x, and f sub 2 of x equals 10 times x. And this is our system of equations. We will go to our graphing calculator. Let me pull that up. Okay, got the calculator back up. I need a new document. You're going to go at this differently than what I have to do on the computer. So we've got a new graphing scheme. I'm going to go to graph. And now I got my f sub 1 of x. And I'm going to put in 4,700 plus 2 times x. It's my first equation. I'll enter that. I don't see anything, but I'm not worried about it yet. I'm going to go ahead and enter my next function and then worry about finding this. F sub 2 of x is equal to 10 times x. I'll enter that one. Okay, I see that one. I know that my intercept is at 4,700, the y value, so that's going to be way, way up there, and it's a positive slope. So everything is going to happen beyond 4,700. You see that, how that's going to be true? So it's going to be out there a ways. I'm not sure how far, so I'm going to go ahead and get up where I can see something and maybe make another decision about the window after I get a look at my window. I could have used some shortcuts there. My x minimum is going to be 0. My x max, I'm not sure. Really, I don't know how long it's going to take for it to get up there. So I think I'm going to put 500 for right now. My y minimum, I know I don't really want to see below 4,700, so I'm going to make that my minimum, 4,700. And my y max, I have no idea. I'm going to put in 10,000. Click OK. And boy, even at that, I'm not seeing it. I can barely see the x values. So let's go, well, the 10,000 doesn't look reasonable, so I'm going to get rid of that, but I need to go farther out in the x direction. So my window settings, I'm going to still, I think I'll keep my x minimum where it is. I'll make the x max 1,000. I'm going to bring my y max down a little bit, 7,000. Click OK. Okay, well that's better, right? I've got an intersection. Yay. And I've got my two functions. So now with my intersection, I'm going to go in and say Analyze Graph, intersection. I'm going to bracket it. And in a very confusing way, I'm just moving the graph so I can see it. And it's 588 is x. So 588 is my x value, and my y value was given as 588 times 10 to the third, and this is actually an approximation. It's close, but not quite. And so my y is approximately, and which is equal 10 to the third means I move my decimal point over. Excuse me, it was 5.88, so that's going to be 5,888 or 5,880, and those are approximate values for our intersection for these. Since I'm dealing with customers, I would want an integer value. I might have to go up or down to get that. So that's it for 10-1. I hope it's helpful. We're going to get into more systems. Yes, we're going to look at other ways to solve a system. Graphing sometimes is a great way to do it reasonably quickly. It's also a marvelous way to check your results when you're using other methods. Good luck on the mastery quiz. See you in class.